Hey, we're back. Thank you. Now we have Alessandro Grande. He's the IoT ecosystem manager for ARM, and he's calling in from Cambridge, UK. He's going to be talking to us about TinyML and doing machine learning. Let's see, how does that relate to drones? Wait, let me show you.
I can't see
There you
myself, so I'm
go.
not sure. Am I on?
Yes, you're on.
Oh, hey. Hi,
Go
everyone.
ahead. The mic's all yours. Thank you, Alessandro.
Thank you. So I'm going to share my screen. Just give me 1 second. Okay, cool. So thank you for having me, Ramon. And I'm really happy to be here today and be able to share with you my passion around machine learning on embedded devices. So as Ramon said, I'm a developer advocate and ecosystem manager, and I work for ARM. And let's see if this works, this slide. Okay, yeah. And why am I here? Well, the interesting thing is that because of my job, I'm exposed to a lot of really interesting people and a lot of interesting trends that I see across the industry. And with this comes a lot of use cases that people and industry leaders are actually trying to make a reality. The other point is that I'm passionate about machine learning, especially on embedded devices and the capabilities that this unlocks. I want to share also with you what I've learned in the last couple of years around machine learning on embedded devices and this new world of possibilities that's opening up. So I guess I'm coming from an IoT space, right? So why am I here and why am I talking to you about machine learning on drones in some ways? I think really when we look at the challenges in drones, they're very similar to some of the challenges that we see in other spaces like IoT, for example, or robotics. And these are that we are in a situation where real time is a really important thing, and we have to make sure that we are making decisions on in real time. And the other thing is that the devices that we're operating with or we're using are situated in a very energy constrained environment. You usually are running off batteries. Obviously, you want to try and fly as much as you can, and this enables you. You have to make sure that you are considering that when you're looking at what's running on your device. The other thing is that you are in a constrained memory system, like in a lot of IoT devices. And last, you've got actually a lot of data coming from a lot of different sensors, and you want to make sense of this data. So I really see, in the same way as in the IoT world, I see a massive opportunity here, and that is really embedded machine learning, or how some people like to call it, TinyML. And what is it actually? What do we mean by embedded machine learning or endpoint AI or TinyML? It's actually machine learning that can run on devices with an energy cost below a few milliwatts or around a few milliwatts. What's interesting is that most of you are probably familiar with machine learning, so I'm not going to focus too much on what machine learning is. But one thing I do want to mention is that this can be mind-blowing to some of you. It can seem mind-blowing because actually we used to think of machine learning running on big GPUs or big servers, but actually there are two steps in machine learning. One is the training, and for that you actually need a lot of data, a lot of compute. But then there is also the other side, the inference side, that is basically making sense of the data around you and actually taking actions on them. And that actually can run very effectively on smaller devices, as we will see today. So what are some of the benefits of actually thinking about machine learning on embedded devices? I like to think that there is actually three main ones. One is security and privacy. And why is that a benefit? Well, because think about the fact that every time you shift data and you send it somewhere off chip or somewhere else, potentially on a cloud or on a ground station, in a drone situation, what you're doing is actually sharing that data with someone else or some other entity. Where if you're able to do the processing on the device, you're not sharing that data with anyone. You're keeping it privately on the device. The other really efficient thing that I like to think about when I think about machine learning on embedded devices is actually power and cost. Moving and fetching data is very expensive, and if you're sending data outside of your device, that cost increasingly increases massively. And therefore, the closer you do the processing to the data itself, to where the data is captured, the more efficient and cost-effective it is. The last point is actually reliability. I mentioned before, obviously, in a real-time situation, you want to make sure that what you're doing is actually happening right away, and actually you don't want to be making decisions delayed from what you're doing. So, for example, if you're trying to do object detection to object avoidance, you want to make sure that you avoid your object in time before you hit the object. So you have to make decisions right away, and you know this better than me. And actually being able to do this, taking these decisions closer to the data itself, to the sensor itself, being able to do machine learning on the sensor itself potentially can enable you to do it even quicker. Now, there are a lot of use cases. Everybody talks about machine learning, and it's interesting that actually there is a big range of use cases, starting from GPUs that are really important when it comes to really complex real-time object recognition or person identification. Cortex-A's are the more Linux-enabled devices, ARM devices. Those are able to do a lot of machine learning. Like, for example, Raspberry Pis are able to do computer vision type applications and run very efficiently. But then if we move down the left of this graph, of this table here, we could see how actually there is a lot of use cases that could be covered or could be effectively run on Cortex-M or microcontrollers. So things like vibration detection, sensor fusion, keyword detection, and other things like, for example, person detection. So individually detecting whether a person is in the video or not could be something that could run efficiently on a really small device, constrained device. The other interesting thing is that actually this trend is here to stay, because actually we see that we're coming up with all these different devices, and there's more and more Cortex-M devices being shipped every year. So there's even more chances for all these devices to get into places where they could be utilized more effectively and more efficiently. So I wanted to touch on, when does it make sense to actually do machine learning on endpoint devices? I believe that it makes sense to do machine learning, to think about machine learning on constrained devices when you have data that's messy. So when you're not really sure how to solve your problem, when you probably would struggle to come up with an algorithm, and you're trying to find a solution that's not very well understood yet. So in that case, you could try and see whether a machine learning model could be able to make sense of your data and actually give you results that you want, or make sense of the data and actually help you to take action. So there are different use cases, as we said before. I think it's useful to think about three different use cases categories, and those are really vibration and motion, so any kind of signal outside of voice and vision, and then there is recognition of voice or sound, and images and videos, really. And those are like three different classes of the problem that machine learning could solve on embedded devices. Okay, so now we're moving towards actually the more practical side of the presentation, and in a few moments I'll actually show you a live demo of this happening. So I'm really excited about that. So let's get into the beefier part of the presentation. First of all, I wanted to mention that actually this is a massive ecosystem effort. It's not just one player that's enabling this technology to actually work and to actually be efficient and effective. It's actually an ecosystem of partners. And you can see here, really, there is a lot of partners that are focused on the software side. So algorithms, software tools, RTOS partners, and all other software partners. And then there is the silicon partners, those that are actually building the hardware itself. And it's interesting how all these players are actually coming together to make TinyML a possibility. What does it actually look like? What does the flow look like for a developer? Well, if you're familiar with machine learning, you know that there is a lot of different frameworks out there. One of them is TensorFlow, for example. So if you think about a TensorFlow generated model and trained model, you can then think of taking that model and optimizing it for running on an embedded stack. What you use in this is actually a TensorFlow, a Google version of TensorFlow called TensorFlow Lite Micro, so for microcontrollers. By utilizing this on top of an embedded stack, you can then use your favorite tool like Arduino or Kyle Microvision or Embed Studio to actually generate binary code that can be used on your device itself. So I wanted to take you through some of the steps that are important to keep in mind when you're doing machine learning on these constrained devices. First of all, I think it's important to realize that actually you need to pick your device first. You need to be able to understand that actually, in comparison to classical machine learning, actually here you are on a constrained device. So you really have to know what your device is and what capabilities it has. The next bit is actually you need to be aware that you need to pick a model that's compact enough that could run on this device. And the last point here is that you want to make sure that the model has less operations. Now, there is a stage that's called optimization stage, and this really it boils down to making sure that the model that you've created can run on your device. And to do this, you have to shrink the model somehow. There is different optimization techniques, one of which is, for example, quantization. So through reducing the size of the weights and the weights and the other bits of the model to run on your device, you can reduce the size that it occupies and run more efficiently, effectively. So you're doing operations more quicker because now you're doing it on smaller parts of data. So this is really important. What's interesting here is that actually you can do this without losing any accuracy. The last thing I wanted to show you here is that actually, as I mentioned before, TensorFlow Lite Micro is a tool from Google. It's an inference engine from Google that ARM is partnering with to actually optimize the efficiency of the inference engine itself on ARM hardware. So we're partnering with Google to make sure that actually TensorFlow runs efficiently on ARM. And this is what you utilize to actually do the last bit of the porting to your device. So you generate the C code that then you can run on your device. What's really interesting is that already in less than a year, there's been a lot of different hardware platforms that are supporting TensorFlow, TensorFlow Lite Micro, and are running effectively these models on their hardware. So you can see here a bunch of different examples, and one of them that I'll show you today in action is actually the Arduino board that you can see here. A very interesting little board. So now I wanted to get to the actual action, and I wanted to show you that there is a lot of things that you can do today. And actually here I've got a list of tutorials and resources that you can look at. They're all also listed in the developer.arm.com IoT website. You can find them there, but I'll be sharing this slide so you can take a look at these afterwards as well. And now I wanted to run the demo. So I think I need some help from Ramon on being able to run this. So I'm going to unshare my screen, and I'm going to share another screen. Just give me 1 second. Okay, so we're getting ready. So what I'll show you today is really a simple way to get started on machine learning with your microcontroller in a few easy steps. So let's see here. I'm sharing. Okay, so one of the guides that the Arduino team has put together. A lot of work has gone into this guide from the Arduino team, so props to them for doing this. They've put together this really, really easy to use guide that you can use to train your model and to run it on your device. So I wanted to show you basically something that people that are working in ML are quite familiar with is Jupyter Notebook. This is a tool that allows you to train your model and optimize it on the cloud directly without having to build it on your local hardware. So Google has created the Colab that Arduino is actually using in this example. So you can see here, this is actually. You should be able to see, the different steps. So there's a setup step. There is I've already run all this for just before this presentation. I didn't want to run it now just because I'm conscious of time. But it's really a few simple steps. So you can see here what you do is basically you get your data through your Arduino device. You upload it here on the left, and then you're able to train the model. So you prepare the data set first. And then you randomize it and split it into different sets of data. So you have typically your training set that in this case is 60% of your initial data, 20% of validation, 20% of testing that you will use later to do actually the testing. Then you train the model. This doesn't take too long because it's actually running on the GPU, on a big beefy GPU. And then what you could do here is actually the Arduino team has done a really good job by showing you some of the really interesting data on the loss function, for example, that can give you an idea of how well your model is performing. So you can see here the plot of the loss function in my case. And finally, you can run the test. So to see how it's performing. In my case, for example, I trained two different types of motions, turbulence and up-down motion. I'm trying to simulate, for example, a use case in which I'm trying to understand whether my flying device is actually in turbulence or is perceiving turbulence, or it's actually going up and down. And you can see how the performance of this model is actually really, really good. And then here you can convert. The last stage is converting the trained model to TensorFlow Lite, and at the end you're able to generate a code that can run on Arduino itself. So I'm gonna now share the actual. So this is the Arduino code that's running on my device, and Ramon, can you confirm that people can see my camera?
Yes.
Okay, cool. So you should be able to see the Arduino device, and you're seeing now on the camera, on the screen, that by moving this now, I will be able to understand the motion, right? So let's see if this works. Demo gods, please be with me. So let's see. Okay, so if I move up and down, that's up and down, up and down. Let's see if it detects turbulence. Up and down again. And you can see how the accuracy of this is actually quite impressive for being a model that runs on a Cortex M4 in a really, really efficient way. And you can see actually the speed of recognition. I mean, it's actually really fast. The only thing that's slowing it down is that there is a window of data collection that's happening. But you can see how actually it's really good at recognizing whether this is turbulence or up and down. And actually, you can train the same. So you could use the same model here to actually add more classes. So you could potentially train multiple classes to understand multiple types of operations of your device. And obviously, it's taking data from the accelerometer and making sense of that data. And again, data from an accelerometer is usually very messy. And what's interesting is actually this is able to make sense of it without actually much work. I mean, the training here is below a few minutes to be able to do this and get this with this accuracy. So I'm really impressed by the work that Arduino has done, and all this again is running effectively is running on TensorFlow Lite Micro, and it's running in the end optimized on ARM hardware. Okay, so with that, I go back to the slides here. So in summary, I really think that machine learning on constrained devices, TinyML, is actually happening now. So it'd be interesting really to understand all the use cases that could be unlocked in the world of drones. I'd be really curious to understand, the different things the different places where you think you could utilize this type of machine learning, and really reach out and let's collaborate. I'm excited by what's possible, and I'm really excited to hear from you guys what you guys have in mind and what kind of stuff you think could be done with this type of technology. Last but not least, there is a link here if you want to learn more about the different partners and what they're doing. There is we're running some AI tech talks that you can follow by clicking on that link. Okay, that's all. So I think.
Thank you,
Alessandro. Yeah, we can go to questions.
That was really good. I have a few questions. Do you mind stop sharing your screen? And I'll share those questions via Teams.
Sure.
Awesome. So I'm going to just drop the questions here. Thanks to the volunteers that put them together, and thanks for the community to really help us with those questions. Like, they've been really at it since the morning. Alessandro, so we have a few questions here. Feel free to pick the ones that you two that you like the most. I don't think we have time for more than 2 or 3.
Yeah, I'm just looking at the question. So, okay, so there is, I'll just pick the first 2 to start with. So the first one is, what is the difference between embedded machine learning and running the machine learning in an SoC? So, okay, we're talking about the same thing. It depends how big your SoC is, how capable your SoC is. So if you're thinking about Linux-enabled SoC, like a Raspberry Pi, for example, that has a Linux-enabled SoC, you're usually running more beefier models. What we're talking about here is the ability to run these models down to a few milliwatts of power. So the ability to run these models in very constrained devices, and the ability to do it effectively and efficiently. So I guess that's the difference. Is SoCs are there is a wide range of SoCs based on ARM. As I showed a graph at the beginning, there are SoCs that mount different types of CPUs, and what I think is really exciting is the ability to run machine learning on the really tiny SoCs or the really tiny CPUs, the Cortex-M CPUs. So the ones that, I guess, to put it into context of drones, the ones that usually are on the flight controller itself. So the SoC on the flight controller, or SoCs that could be attached to the sensor itself. And I go for the second question as well. Can you train on small devices? So there is some partners that are looking at that and are starting to do some of the training on the devices. Right now, it's probably best if you don't do the training on the device, but you do the training off the prior to the device. And what you could do is feed back some of your data to potentially an external source, so you could refine the model and potentially redeploy a better model in the future. That's the easiest workflow today, but things are moving very fast, and I can see how the training could start happening on device as well. Do I have time for another one? Okay. Sorry, I'm just reading the questions. Okay,
Alessandro,
so yeah. What's the
What
breadth
do
of
you-
ML models we
Go
can
ahead.
use on embedded systems? Are there only computer vision models, or are there more ML models we can use? For example, SVM for sensor fusion. So the reality, as I mentioned before, is that it really depends on understanding the size of the model, and there are some models that are that have a lot of operations, and those are probably not the best models to run on really tiny devices. But there are a lot of different models that are being ported to the embedded devices right now. I shared some of the links to some links to some guides where you can see a bunch of different models. So some that are running, like the one that I used today, that are running fully connected models for vibration, for example, use cases, or in general sensors like accelerometers and stuff like that. And then there is CNNs that are being utilized a lot in computer vision and other models. So there is a lot of research around trying to port different types of models to embedded devices. And then I'll just go with the last one. Can I run TensorFlow Lite on an NXP MX8 Mini? So TensorFlow Lite can be run on multiple platforms. If you go to the TensorFlow Lite Micro website, there is a list of supported devices, and there is, obviously there are ways of porting that to different platforms. So if it's not ported to the device that you're using today, you can do that. Don't forget that the IMX8, for example, has got multiple CPUs. So some of them will run Linux and will run containers and will run, will give you the ability to run machine learning in a different way. And then there are also Cortex-Ms on there. So you could run potentially TinyML on those Cortex-Ms.
Awesome. Thank you, Alessandro.
Thank you. It was a pleasure.
All right. Hey, guys. Welcome back to the PX4 Developer Summit. Your host here, Ramon Roche. Thanks, folks, for your help with the questions. Team effort, right? Thank you, Alessandro, again. Super cool demo. Please share the link on Slack with all of us. There's a lot of more questions for Alessandro, so maybe you want to join us on Slack and do a live Q&A there.